Alex is here.
And MoNaCo is too.
All right, Unit 9, Kinetics and Equilibrium.
Right. This is going to be another quick unit. Get
Yeah.
with it.
Marking period ends in 2 weeks, guys.
Get with the pace.
So, start on page 3.
Let's do our objectives. What do you need to know? Check them off as we go.
Yes. All right, we have 3 major topics in a unit.
Kinetics, thermodynamics, and equilibrium.
Okay, good.
Very straightforward.
The things in kinetics we need to know.
You got to know what a reaction rate is and what governs that reaction rate relating to collision theory, reaction mechanisms, and how you can affect the reaction rate, like how you can make it faster or slower.
And these are the 6 specific things we can do. We can change the nature of reactants, concentration, surface area, pressure, catalyst, and temperature.
Do all those changes and magic on your reactants, you're going to make your products faster or slower.
Correct.
And that's what the whole kinetics is. The speed of a reaction going from reactants to products. How quick does it happen? How can you speed it up? How can you slow it down? End of story. Oh, and why it happens. That's the collision theory.
Right.
And the mechanism.
Well, what we'd like to do is relate all 6 of these things back to collision theory.
Right.
By doing them, I make more collisions, and that's why it goes faster. So that's the connection that we make. And just while we're here, all 6 of those examples, testable.
Most definitely.
All right, thermodynamics. Thermo, heat. So that's really what we're going to get into here, right? The heat that kind of drives the reaction.
Yeah, like heat again. But not QMC delta T heat.
No.
Not heat in a chemical reaction. We're talking about changes in heat in a chemical reaction with respect to the potential energy changes that occur.
Yeah, like really like stored chemical potential energy that exists within the bonds.
Right.
And low energy is what we want.
We're going to see the heat of reactions table again.
Yep.
We're going to see endothermic and exothermic reactions again.
We're going to learn about some new things.
Like the potential energy diagrams, we're going to go into the details of where the activated complex is, what the activation energy of the forward and the reverse reactions are, and the effects of adding a catalyst to the reaction on what the potential energy diagram would look like.
Yep.
So memorizing the important parts of a chart, it's basically going to be there.
Yeah, and even a step farther than memorizing, because unfortunately, we'll see when we do them, I can change where on the chart I put that label, and you got to know enough about the label's definition, or the graph's definitions, to relabel it in different places.
Right.
So that gets tricky. So
Now, equilibrium is the other important part of this.
sounds a lot like equal.
And it's about equal rates. So we started studying kinetics, forward reactions, how you can speed them up or slow them down. Equilibrium means there's a forward and reverse reaction happening at the same time.
So as 2 reactants come together to make a product.
And that product also comes back apart to make the reactants in the beginning. It's like ping pong.
It's like a cycle.
At the same time. It's like,
Yeah.
Imagine playing a game of ping pong with 2 ping pong balls.
There you go.
Each player hits a ping pong ball at the same time. They pass each other over the net at the same moment, and then back and forth and back and forth. You have
That really is equilibrium. And then this concept later on, Le Chatelier is how we say that. Basically states that the equilibrium itself will make an adjustment to regain equilibrium if we stress it.
all again connecting back to collision theory.
Yes.
The reason why the temperature changes and pushes an equilibrium in one direction is because the temperature changes the rate of a certain reaction, either the forward or the reverse reaction. And so the reaction will shift, the equilibrium will shift in a direction, the products or the reactants.
Yes. And then with 2 new, well, one's not so new, but 2 new vocab words looking very much the same.
Ooh, yeah.
Entropy and enthalpy.
Right.
And entropy, man, I don't know, I really dig entropy. It's one of those concepts.
I should have put these boxes under thermodynamics because these are governing bodies and the rules why reactions even start in the first place, like spontaneity and stuff. Like the universe is playing the laws of thermodynamics in that it wants the enthalpy, the heat of all chemical reactions, to go to a lower state.
Right. And
release energy.
Entropy is the measure of disorder, and it actually, the universe likes disorder.
Things like gravity go against it, but that's what it is. It's about balance and equilibrium in the universe, right?
Right. Because, well, let's be honest, it takes energy to order things. If you think about cleaning your room or building a Lego castle, you got to put a lot of energy in.
I mean, why does once you put a spark to a piece of paper, does the entire piece of paper burst into flame? Because of enthalpy and entropy. When the paper burns, it releases all the heat that's been stored up in the chemical bonds. So it goes to lower enthalpy, lower heat. The universe likes that, so it keeps feeding itself, going, going, going. Entropy, all the ash and smoke and stuff that is produced because of the piece of paper burning, has got more chaos, random, and disorder than the piece of paper had in the first place.
It was all stored and ordered and next to each other and in
so
line.
The universe appreciates that too. So once it's started, once you activate the reaction with a little activation energy, it's going to keep going until it runs out
of reactant
because of entropy and enthalpy and thermodynamics.
Beautiful. Well, that's it for this video, guys. Keep an eye out for each of these topics. Feel free to check them off as you go and master them, and that's it. We done.